Hello everyone, welcome to this fourth lecture of this topic, finite element analysis. This is Mr. Suyog Patil, Assistant Professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Hyderabad, Ichalkaranji. Today we are going to discuss this plane stresses and plane strains in finite element analysis. So first of all, we will discuss this lesson outcomes. Okay. At the end of this lesson, the student should be able to understand the plane stress, what is mean by the plane stresses, what are the conditions for these plane stresses. Then student should be able to understand the plane strain conditions. Then again, student should be able to develop the plane stress and plane strain stiffness equations. Or again, we can say the plane stress and plane strain matrices. Okay. So before discussing this plane stress and plane strain, first of all we will discuss these 2D planar elements. Okay. In the previous lecture already we discussed that different types of these elements. Okay, 1D element, 2D, 3D, solid elements, likewise. Okay. Now these 2D elements, the both the plane stress and plane strain conditions can be modeled by using these 2D plane elements only. Okay. These 2D elements are used to model these plane stress and plane strain conditions. Okay. Then again, these 2D planar elements are defined by at least three nodes in a two-dimensional plane, that is x and y plane. Okay, in two-dimensional x and y planes, these 2D elements are at least it is required three nodes. Okay, to define these 2D elements. Then these elements can be connected at common nodes and or along a common edges. Okay, then these 2D elements, planar elements, can be connected at common nodes or along the common edges. For example, 2D triangular elements. Then again we can say 2D rectangular or square elements also there. Okay. Then again some of the examples such as that structures that can be modeled using 2D elements include long structures with constant cross section, or such as a dam or pipeline. Okay, then again deep beams or plates with holes loaded in the plane. Okay, these are the some examples of the plane stress and plane strain, plane strains. Okay, so this we will discuss in detail. Then again these 2D elements, it is made sure during the formulation that the compatibility between model displacements is maintained. Okay, so these 2D planar elements, it should be made sure that this formulation should be made compatible between the nodal displacement. Okay, and this is achieved through ensuring the selection of the suitable shape function. Okay, so therefore we should select a suitable shape function and we should achieve this nodal displacement compatibility. Okay, then again this compatibility along common edges is maintained by choosing proper displacement functions. Okay, again by selecting proper displacement functions we can maintain this compatibility in the 2D planar elements. Okay, then these elements are used for example, these 2D elements are basically used for plane stress analysis and plane strain analysis. So in this plane stress analysis, this analysis performed for structures loaded in their plane, such as the plates with holes. Okay, so plates with holes, and when there is loading is applied on that planes, so that condition is, or we can say the plane stress will be there. So therefore in such a cases these 2D elements are used. Then in plane strain analysis conditions, it is performed generally for long structures subjected to constant load along their length, such as dams, culverts, etc. Okay, in case of these dams, the length of this dam is higher compared to this width and height. Okay, so again in such a conditions or such cases, and the constant loading is there on this dam. Okay, so in such cases, these cases can be assumed for plane strain analysis. Now, first of all, we will discuss what is meant by plane stress. Okay, so this plane stress is defined to be a state of stress in which the normal stress and the shear stresses directed perpendicular to the plane are assumed to be zero. Okay, so here in plane stress applications, it is assumed that the normal stress and shear stress perpendicular to the plane are 0. Okay, it is assumed that this perpendicular stresses are 0 here, or again we can say here. So this is the a plate having a hole at the center. Okay, and here some tensile loading is there. Okay, along this x direction. So therefore some sort of the stress will be there along this x axis. Okay, sigma x not equal to 0 means there is some stress along the x axis. Sigma y is not equals to 0 means there is something value of the stress along the y axis as well as. Okay, and tau xy is also not equals to 0, but the sigma z, tau xz and tau yz is equals to 0. So that means the stress along this z axis is 0. Okay, again here also same, it is tensile stress along the x axis, y axis is present, but stress along the z axis is absent here. Okay, that means the perpendicular stress perpendicular to this plane is 0. Okay, so this is the section plane which is shown here. Okay, elemental sectional plane. So the perpendicular stress is perpendicular to this plane is 0. Okay, then again generally members that are thin, those with a small z dimension compared to the dimension in x and y dimensions. Okay, and whose loads acts only in the xy plane can be considered to be under plane stress. Okay, so whenever there is a small application or small member, okay, having z dimension is very small as compared to x and y direction. Okay, here we can say this is the y and this is the x dimension of the member, and this thickness is the z dimension of this member. Okay, and this thickness is very small as compared to this width and height. Okay, so therefore in such a cases this plane stresses will be there. Okay, that means the perpendicular stresses will be 0. It is assumed that there is no stress or 0 stress in the direct and shear stress in the perpendicular plane. Okay, so this is the case of the plane stress. Now condition. Okay, so in this plane stress, this is a state of stress. Okay, when all the stresses act in a single plane, that is direct as well as the shear stresses perpendicular to the plane are 0. Okay, the stresses, direct stress or shear stress perpendicular to the plane are 0. That is the condition of this plane stress. Okay, so that means here we can see sigma z, tau xz and tau yz is equals to 0. That is perpendicular plane stress is 0. Then generally thin structural members loaded in their plane are considered to be in plane stress condition. Okay, then we will see plane strain. The plane strain is defined to be a state of strain normal to the xy plane, that is this strain in the z direction, and the shear strains gamma xz and gamma yz are assumed to be 0. Okay, so in this plane strain condition we can say the strain normal to this xy plane or strain normal to this xy plane, that is the perpendicular to this section plane is 0. Okay, it is assumed that this strain is 0 in this case, and in this plane strain conditions the example of this plane strain condition is a dam. Okay, where the constant loading is there. Here the force acting on this dam is constant. Okay, for along the throughout the length of the dam. Okay, so therefore strain perpendicular to this plane is, it is assumed that 0. Okay, and this is the case of the plane strain condition. So again here we can say this is a long cylinder under uniform loading. Okay, in this case also, so some load is there acting on this cylindrical surface. Okay, on this cylindrical surface load is acting, and the strain along this plane that is along the z direction is 0. Okay, some sort of the strain is there along x and y axis, but along the z direction it is 0. It is assumed that it is 0, perpendicular to 0. Okay, similarly here it is also, we can say this constant loading is there throughout the length of this semicircular semi-infinite region. Okay, and constant uniform load is there here. Okay, but the strain along this perpendicular direction along the z axis is 0 here. That means strain along this direction, z direction, is 0. Okay, see, this is the example of the plane strain. Then condition, plane strain condition. Okay, if there are no strain out of the plane, that is the strains perpendicular to the plane being considered, or any component, therefore are all 0. Okay, then this condition is called as plane strain condition. So we can see here this Ez strain along the z direction, or we can say this gamma xz and gamma yz are equals to 0. Okay, all these are equals to 0. Then this happens in long bodies with constant cross sectional area and loads acting in x and y directions only. Okay, and when a constant value along the z direction. So this plane strain happens, or this plane strain exists when there is only x load is there in only in x and y directions. Okay, and the constant value of this load is along the z direction. Then also only a unit thickness of these structures is considered for analysis. Okay, because all unit thicknesses except near the ends of the structure behave identically. Okay, we can see here constant loading is there, and it's a cross sectional area is also same here. Okay, so therefore we can assume only one elemental area here at this end. Okay, and we can perform this analysis because this thickness is constant throughout the length. Okay, then stress strain matrix. Okay, so as we know, this stress is equals to, stress is directly proportional to this strain. Okay, so therefore this stress is equals to some D matrix, or it is also called as constitutive matrix, into strain matrix. Okay, stress matrix is equals to, so therefore this matrix D is called as stress strain matrix. Okay, this D matrix is called as stress strain matrix, or sometimes it is also called as constitutive matrix. Okay, and in case of this plane stress, this D is equals to, D matrix is equals to E, that is Young's modulus, divided by 1 minus mu square, mu, where mu means this Poisson's ratio. Okay, into this matrix, that is 1 mu 0 mu 1 0 0 0 1 minus mu divided by 2. Okay, so this is the D matrix, that is stress strain matrix for plane stress condition. Okay, where E is the Young's modulus and mu is the Poisson's ratio. Okay, and for the plane strain condition, this strain matrix is, and this D changes to, therefore this D is equals to E divided by 1 plus mu into, in bracket, 1 minus 2 times mu. Okay, into this matrix, that is 1 minus mu mu 0 mu 1 minus mu 0 0 0 1 minus 2 times mu divided by 2. Okay, this is the D strain matrix for plane strain condition. Okay, now we will see this stress and strain matrix equations or derivation we will see here. Okay, so in this example, this 1D bar element, okay, this bar is considered here, and 1D bar element, and in this figure, this bar element having two nodes, 1 and 2. Okay, this is the first node and this is the second node, first and second node bar element, whose coordinates are x1 and x2 in Cartesian coordinate. Okay, in this Cartesian coordinate system, the first and second node and their coordinates are x1 of the first node, and here it is x2, from this point to this point it is x2, and that is the coordinates of the second node. Okay, and in natural coordinates, the position of the nodes are zeta is equals to -1 and zeta is equals to +1 respectively. Okay, in this natural coordinate system, zeta is equals to -1 is the coordinate of the first node, and zeta is equals to 1 plus 1 is the coordinate of the second node. Okay, so these are the two nodes and their positions in the natural coordinate system and Cartesian coordinate system, okay, of this 1D bar element. Now, but the strain in an element is strain E is equals to dou U by dou X. Okay, where this U is equals to the displacement. Okay, this U1 is the displacement at the first node, and here U2 is the displacement at the second node in the natural coordinate system. Okay, as well as in the Cartesian coordinate system, this U2 is the displacement at the second node, and whereas this U1 is the displacement at the first node. Okay, then again we can say this x2, okay, this second coordinate x2 minus this first coordinate x1, okay, this when we take this minus, this is the length of this element. Okay, so this length of the element is equals to x2 minus x1. Okay, x2 minus x1 is the length of the element. Okay, now we can see here this strain is the strain in an element is the derivative of this displacement function. Okay, so dou u by dou x. Then again this element strain in terms of partial derivatives of this displacement with respect to this zeta is given by, okay, we can rearrange this equation of the strain. Okay, therefore this strain E is equals to this dou u by dou zeta into dou zeta divided by dou x. Okay, this dou zeta will cancel, dou u by dou x, that is sigma, sorry, E is equals to dou u by dou x here. Okay, we have rearranged this term. Okay, but again we know that the field variable u, okay, so therefore this field variable here in this example, this variable is u, that is displacement. Okay, displacement at node 1 and displacement at the node 2. Okay, and that field variable u is equals to n1 into u1 plus n2 into u2. Okay, whereas this n1 and n2 are the shape functions. Okay, n1 and n2 are the shape functions at the field variables, and u is the field variable, that is displacement. Okay, so again this n1 and n2 are, n1 is equals to 1 minus zeta divided by 2 and n2 is equals to 1 plus zeta divided by 2. In case of this natural coordinate system, these shape functions are 1 minus zeta divided by 2 and 1 plus zeta divided by 2. Okay, so therefore by putting these values of n1 and n2 in this equation, u is equals to n1 u1 plus n2 u2 in this equation, so we will get this equation. Okay, so therefore u is equals to 1 minus zeta divided by 2 times u1 plus 1 plus zeta divided by 2 times u2. Okay, this is equation. Then again take a partial derivative of this equation with respect to zeta. Okay, with respect to this variable dou zeta. Okay, so therefore dou u by dou zeta here, dou u by dou zeta is equals to the derivative of this 1 minus zeta divided by 2 is minus 1 by 2. Okay, so it is minus 1 by 2 times u1, that means minus u1 by 2. Okay, then plus 1 plus zeta divided by 2, the derivative of this bracket is 1 by 2. Okay, the derivative of zeta is 1 with respect to zeta, and it is divided by 2. Okay, so therefore 1 by 2 times u2, that means plus u2 divided by 2. Okay, which is equals to this u2 minus u1 divided by 2 here. Okay, this equation is simplified here, so therefore this dou u by dou zeta is equals to u2 minus u1 divided by 2. Okay, this. Now again this relation between this Cartesian coordinate system and natural coordinate system, that is x and zeta. Okay, as we know this zeta is equals to 2 times x minus x1 divided by x2 minus x1 minus 1. Okay, so this is the relationship between this natural coordinate system and Cartesian coordinate system. Okay, so again by taking the derivative of this equation zeta with respect to dou x. Okay, so therefore dou zeta divided by dou x is equals to derivative of this is 2 divided by x2 minus x1. Okay, because of this x is the derivative of this x is with respect to dou x is 1. Okay, so therefore 2 divided by x2 minus x1, which is again equals to 2 divided by LE. Okay, where this x2 minus x1 is the length of the element as we seen in the previous slide. Okay, this x2 minus x1 is nothing but the length of the element. Okay, so therefore this dou zeta divided by dou x is equals to 2 divided by le, length of the element. Okay, now by putting this value of dou zeta divided by dou x and this value of dou u by dou zeta in this equation, that is in the strain equation. Okay, strain E is equals to dou u by dou zeta, this dou u by dou zeta into this dou zeta divided by dou x. Okay, by putting all these values, so we will get this equation. Okay, that is strain E is equals to u minus u1 plus u2 divided by 2 into this 2 divided by le. Okay, so by simplifying this equation again, this 2 will get cancelled here. Okay, so therefore this u2 minus u1 divided by le. Okay, or again we can say this strain E is equals to minus u1 plus u2 divided by le. Okay, this equation we will get the equation of the strain. Okay, see E. Then again this equation of the strain E is equals to minus u1 plus u2 divided by le. We can write down this equation in matrix form. Okay, so therefore this strain matrix, strain E is equals to, strain matrix is equals to, this le is constant here. Okay, le is constant, so therefore 1 divided by le it is taken. Okay, 1 divided by le it is outside, then minus u1 plus u2. Okay, so therefore in terms of this matrix form it is taken as minus 1 and 1 here. Okay, and this u1 and u2 are taken outside. Okay, in this matrix u1 and u2. Okay, by simplifying this matrix or by multiplication of this matrix we will get this minus u1 plus this u2. Okay, divided by 1 upon le. Okay, so therefore this is the equation of the, or this is the strain matrix. Okay, strain matrix E is equals to 1 upon le into in bracket minus 1 1 u1 u2. Okay, this is the strain matrix. Then again the strain matrix, it can also written as the strain matrix E is equals to matrix B into matrix U. Okay, where this matrix B is the strain displacement matrix. Okay, it is also called as strain displacement matrix or B matrix. Okay, B matrix. So therefore this B matrix is equals to this 1 upon le into minus 1 1. Okay, 1 upon le minus 1 1 is the strain displacement matrix, and this U is the, this u1 and u2 matrix. Okay, that is displacement matrix. Okay, now stress matrix, this is now we discuss the strain matrix and now it is stress matrix. Okay, then again from Hooke's law it is, we know that the stress divided by strain is the Young's modulus. Okay, this stress divided by strain is the Young's modulus. Okay, so therefore this sigma divided by this E strain is equals to capital E. Okay, so therefore this sigma stress is equals to Young's modulus into strain. Okay, that is strain small e into Young's modulus capital E. Okay, then so therefore this stress sigma is equals to this capital E as it is and into this strain. Okay, that means this strain is equals to B matrix into U matrix. Okay, B matrix into U matrix. So therefore this is this stress matrix for 1D bar element. Okay, this sigma is equals to capital E Young's modulus into this strain matrix B into U. Okay, this is the stress matrix. Okay, then again we can see here the similarly after solving these equations of strain energy for the element we will get an elemental stiffness matrix. Okay, now after calculating this stress matrix and strain matrix, then we have to calculate the elemental stiffness matrix. Okay, elemental stiffness matrix, and by solving the equation of the strain energy for this element, so we will get an elemental stiffness matrix Ke is equals to Ae divided by Le into in bracket 1 minus 1 minus 1 1. Okay, so this is the elemental stiffness matrix. Okay, this is the elemental stiffness matrix for 1D bar element. Okay, elemental stiffness matrix for 1D bar element. Okay, friends, thanks for watching this video. If you like this video, please share, comment and like this video. Then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.